Our topic today is a new discovery that's been made by the Interstellar Boundary Explorer, which is put into NASA speak by calling it IBEX, a mission. This mission has produced some brand new results that give us our very first look at our home in the galaxy. Now, the results that you're going to see today come from a very broad collaboration between several NASA missions, a fusion of industry, academic, and government resources, and international partnerships. Now, in my view, this collaboration, while not our main story, is a remarkable model of how current space physics research is conducted, with the twin goals of achieving both excellence and integrity in the scientific research. Now, today's panel reflects this broad collaboration. With us today is a distinguished group of experimenters and investigators who will present this newest result of our home in the galaxy, and they are Eric Christian, who is the IBEX Deputy Mission Scientist, and he's from Goddard Space Flight Center. David McComas. Dr. McComas is the Interstellar Boundary Explorer, IBEX, spacecraft principal investigator, and he is also an Assistant Vice President of the Space Science and Engineering Division of the Southwest Research Institute in San Antonio, Texas. Next to David is Dr. Rosine Lallemant. She's the senior scientist at the French National Center for Space Research. Sitting next to Rosine is Lindsay Bartolone. She's the IBEX Education and Public Outreach Lead and is with the Adler Planetarium in Chicago, Illinois. And at the end, the far end, we have a dual, kind of a defensive, offensive player, two sides of the same coin. He is a Cassini spacecraft instrument scientist and IBEX co-investigator. That's Dr. Don Mitchell from the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. And I'm going to ask Eric if he would start today's presentation.
Thanks, Dick. Well, this is an amazing time to be studying the outer heliosphere. In the last few years, both Voyager spacecrafts have passed through the first boundary between our solar system and interstellar space. And they're out there now measuring this interaction region. They're measuring solar wind, pressure, temperature, velocity in this interaction region. And now IBEX comes along and fills in all the places that Voyager isn't. Now, what is the heliosphere? If you watch this movie here, there's a 1,000,000-mile-per-hour solar wind, hot gas that blows out from the sun in all directions. And that solar wind has actually blown a bubble in interstellar space. That bubble has a bunch of different layers. There's an inner region, mostly spherical, where the solar wind is moving very quickly, and then it slows down drastically at what's called the termination shock and flows down into a long comet-shaped tail. It's in between this termination shock and the boundary that the Voyagers are right now measuring. And then there's actually an interstellar wind that's pushing on the heliosphere from outside and flowing around this comet-shaped heliosphere. So we're going to show you some new results from IBEX. And to set the context, I'd like to show this picture here. We've got to take this map where we're looking out from very close to the sun on this entire region. And the way we do that is we flatten it out with the two-dimensional map projection. This picture is the way the night sky would look if you could see the entire night sky. The Earth wasn't blocking half of it. And the big bright band that goes through it is the Milky Way galaxy, what's called the galactic plane. And it's a ring in space. It goes around your sphere that you're looking out on, but the map projection turns it into this S-shaped band. So you can see the local stars, and now if you run it, we can show you where the two Voyager spacecraft are on this projection. And here you see Voyager 1 and Voyager 2, where their positions are, and the nose is the direction that the sun is moving relative to interstellar gas. It's the upstream direction. And all of our map projections coming up are going to have pretty much the nose centered and be in this form. So we have Voyager 1 and Voyager 2, and they're like weather stations. But can you imagine trying to determine the weather on the entire Earth from 2 weather stations? You can't do it. IBEX is like our first weather satellite and gives us the full picture. And so to fill in all the stuff that you don't see on this picture here, Dave McComas.
Thanks, Eric, and good afternoon. So I'll pick up the story exactly where Eric left it off. We have these fabulous observations from the 2 Voyager spacecraft out in this interaction region at the edge of our solar system, our heliosphere. But there are only these 2 locations, these 2 very specific locations in space. And so what you see on this graphic is the picture of our heliosphere, the global picture of our heliosphere as it was yesterday, with just these two points. And now, if we run the fade, you'll see the new picture, the picture of what we know of our heliosphere today. These results are from IBEX. They're neutral particles, neutral atoms coming in from the very edge of the heliosphere. What you see is a very bright and very narrow ribbon of particles coming in, neutral atoms coming in. The expectations from theorists and modelers were that there'd be small variations, tens of percent across these sorts of regions of space, but instead we see 200–300% variations across this ribbon. And so this is a shocking new result for us, and one that's, even as we speak now, not entirely understood and not entirely explained. But it's a very exciting result for us, and it shows that what we thought we understood before about this interaction is definitely not right, and we have to kind of go back and start over. So I'm going to talk a lot more about the observations and about the ribbon, but before I do that, let me give you a little bit of background about IBEX and the spacecraft and how we take the measurements, because it's important to understand what we're seeing. So in this movie, you'll see the IBEX spacecraft. This is an artist rendition. The IBEX spacecraft is a very small spacecraft. This is actually a full-sized model over here. It's about 3 feet in diameter, 1.5 feet tall. It weighs about 200 pounds. It's got one side that points towards the sun. It spins at 4 RPMs, 4 rotations per minute. And the top side, blue in the movie, you're basically seeing the solar panels. Well, we have 2 very large sensors, cameras, actually cameras not of light, but cameras of neutral atoms. And we look out the 2 sides perpendicular to the spin axis, and we view these two directions in space. And every time the spacecraft spins, we're able to make these observations. Before I get into that in more detail, let me talk a little bit about where these neutral particles come from. Ultimately, these particles mostly come from the sun, from the solar wind. Eric already mentioned the solar wind, this million-mile-an-hour gas that goes spreading out from the sun all the time. If we run the movie here, we'll start with the sun. So here you see a picture of the sun. We move in close into the solar corona, million-degree corona. And this atmosphere, this corona, boils off into space and produces this million-mile-an-hour wind all the time of hot ionized gas. As those particles flow radially outward, they drag out the magnetic field from the sun. And when they get out into this interaction region, as you see here, and we'll blow that region up, they actually are tied to magnetic field lines, because all charged particles are tied to magnetic field lines. So they go around and around, gyrating around the field. And sometimes they come close to another particle and steal an electron. And when they can steal an electron, they go zipping off in whatever direction they were going. And some of them go right back in towards us and go right in the aperture of the IBEX spacecraft. And I like to think of that as sort of a 10 billion mile away hole-in-one for one of these neutral atoms coming in from the boundary of the solar system. So we talked a little bit about how the ENA cameras, energetic neutral atom cameras, look off the 2 sides. That allows us to see a swath of the sky as the spacecraft spins. And in the graphic that we have here, go ahead and run that, please. You can see the 2 fields of view, these 2 pixel fields of view, looking off to the 2 sides. And as the spacecraft spins around, each of IBEX high and low views all the way around in this great circle and takes excellent measurements of the ENAs coming in this circle. Okay, but that's not a sky map. We had to find a way with this small, cheap spacecraft to actually see all of the sky. And so we used something that we naturally had. We only have one side that has solar panels on it. And so what we do is we point that side towards the sun. And as the Earth goes around the sun, and let's run this next graphic, as the Earth goes around the sun, we keep repointing the spacecraft so it's pointing towards the sun. If you can roll this movie, please. And as we repoint the spacecraft, the swath of the sky that you observe rotates around. And so you end up basically, over the course of half a year, by the spinning of the spacecraft and the repointing of the spacecraft, observing all directions in space. Okay, so that's how we view these energetic neutral atoms, how we can see them coming from all directions in space. I'd like to start the next movie. It shows IBEX in orbit around the Earth. IBEX is actually making these measurements from an Earth orbit. It's a very high altitude Earth orbit. We go almost all the way out to the moon, about 50 Earth radii, and then come back in. It takes about a week for IBEX to orbit around the Earth and make a full orbit. Over that week, we're at high altitude for most of the time, measuring these neutral particles, and then we come in close, we downlink our data. Now we're going to back away from this view, and as we back away from this view, you're going to see that that's the Earth. We're going to now see the orbits of Venus, of Mercury, the Sun itself, and you can see the direction of motion through the local interstellar medium, and painted in the backdrop, you can see these measurements that we've just made of the ribbon. So we're inside a sphere looking around in all directions and measuring these particles coming from all directions. If we back out of that sphere and see it from the outside, you can imagine taking a knife and cutting through that sphere and opening it up and flattening it out onto a page. And that's the sky map that you're seeing, and all of the observations we're going to talk about are in this format. So the nose is at the middle, that's the direction we're going through the galaxy. The tail is on the far right and left. North and south poles are where they are. So IBEX doesn't only measure particles at one energy, but actually measures particles over a broad range of energies, from about 10 electron volts all the way up to 6,000 electron volts. And this next graphic that you're going to see is actually a set of 5 sky maps, not just one, but 5 sky maps at different energies. And they correspond to neutral hydrogen atoms coming in with speeds between 500,000 miles an hour and about 2.5 million miles an hour. And what you see as we sort of go through, fade through the different energies, is that this ribbon changes and appears to get broader as you move away from 1 kilovolt, about 1,000,000 mile an hour particles. It's actually not getting broader. What's happening is it's not as bright compared to the background, and so you're sort of seeing the background, the distributed flux from around there coming up. There are a lot of really fascinating things in these measurements. You can see in this one, for example, a bright spot up at high latitudes on the left-hand side, which has a very different sort of a feature than much of the rest of the ribbon. So there's a lot of really great detailed information in these sky maps. Another thing that we scientists always want to do is we want to be able to confirm our results, and that's especially important when we find something that's not what we expected, that doesn't agree with theory, doesn't agree with model. How do you know you're right? How do you know that you can really trust these results? And so IBEX, by its very design from the beginning, has these 2 sensors, IBEX high and low, measuring 2 different energy ranges, but we overlap the energy ranges in a way that we were able to measure in the most important energy range at about 1 kilovolt. We were able to measure independently with the two instruments. And so the graphic that we've put up now shows on the top the IBEX high sky map at 1 kilovolt, 1.1 kilovolts, and the IBEX low sky map at about 1 kilovolt. Very similar energies. And while there's much better statistics in the IBEX high sky map on top, clearly the ribbon is present, is in the same place, and has the same sort of characteristics as measured by IBEX low. So these measurements are completely independently confirmed by IBEX itself, and you're going to hear a little later in this press conference, they're also confirmed and in fact extended with the Cassini observations, which Don will talk about shortly. So it would be shocking enough if what we found was a ribbon that was tens of degrees wide, 10, 20 degrees wide. But it's even more shocking than that, because when we look with really high resolution, and IBEX has the sensitivity to really look at very narrow angular resolution, we actually see fine structure. And the graphic that we've put up here takes a piece of this ribbon south of the equator and blows it up. And in addition, what we've done now is we've binned up the individual particles that we observe coming in half-degree bins, and we've summed those half-degree bins until we get about 100 counts in a bin, which is a good statistical number. When you do that, what you see is the ribbon itself has got a lot of fine structure in it, that there are actually structures in there that are much brighter than the adjacent things, that are only a degree or 2 or 3 degrees wide. That's really shocking when these things are coming from a region that's so large and so distributed. And nobody expected to see anything like that fine structure. So I just wanted to mention there are a lot of other great results coming out of IBEX. We have 5 papers that are just coming out in Science right now, posted online right now with this press conference, a 6th from the Cassini measurements. They cover a lot of different areas. I wanted to mention one more area for you, and that's the direct detection of interstellar neutrals. In addition to these neutral atoms, which are created in the interaction region at the boundaries of the heliosphere, there are also very low energy neutrals that are just wandering into the heliosphere as we move through the galaxy. And previously, spacecraft observations had seen helium directly. But with IBEX, we've now made and have just published the very first observations, direct observations of interstellar hydrogen and oxygen, in addition to observing helium. And in the graphic that's put up now, you can see those three. These are from the low energy detector, IBEX low. And you can see these quite localized bright spots that are produced by the different species. And they come from a time when IBEX is in exactly the right spot in the orbit that the particles coming in from the interstellar medium feel the force of gravity, are bent around, and come right into the aperture. And so it's yet another type of observation of this interaction that we're making. So with my final graphic, I want to answer the question, so what is this ribbon and what does it mean? Unfortunately, I can't answer that question because we don't know what this ribbon really is. We know some interesting things about it, though. As soon as we saw this, and we're building up the sky maps week by week, and we see this bright thing, like, wow, what's that? And it goes around and it starts to wind up, and holy moly. So as we're looking at that, and as it's building up, people start to say, what could it be? What could it correlate with? And we pretty quickly realized that the external magnetic field in the galaxy, the local part of the galaxy, what's called the local interstellar magnetic field, was oriented in just such a way that it seemed to organize these data and correlate with the ribbon. And in the graphic that we've put up here, you can see the sort of a picture from the outside looking in. We've painted the ribbon and the particle fluxes on this boundary of the heliosphere. And then we've put in the expected orientation of the external magnetic field. And you can sort of think of that external magnetic field like a bunch of bungee cords. If you're pushing a beach ball through bungee cords, it kind of drapes around and pushes in on the beach ball, but it also changes the shape of the bungee cords. And that's sort of what magnetic field lines are like. And so what you see here is the external magnetic field pushing in the southern hemisphere of the heliosphere, and also pushing in and squeezing it from the sides. And just exactly where it's most bent and most draped around the outside is exactly where the ribbon is lying. Really a remarkable correlation, and almost surely telling us that somehow this external magnetic field is really playing another dominant role in the interaction. But we don't understand the physical connection. We don't know why having an external field that drapes around that way and pushes on the outer boundary that way really produces these 200, 300% higher fluxes than the surrounding regions. And that's a really exciting and interesting part where we now have to go back and try to figure out what physics we're missing in all our models and understanding. And so with that, I'd like to pass it over to Rosine Lallemand, who's an expert in the environment around our heliosphere.
Thank you, Dave. Let's go back to the location of the sun in our galaxy. And you may wonder whether such a galactic wind able to stop the solar wind and confine it within our heliosphere is a common situation. And the answer is yes. And as you can see in this movie showing the galaxy is rotating, but it is not rotating rigidly like a solid body. Instead, all the stars and the clouds of gas and dust, they are all moving with respect to each other. This is due to the constant recycling of the matter, stellar formation, explosion, etc. So this is as a consequence, our sun is moving with respect to the ambient medium. Presently, our star is crossing a very small interstellar cloud, and this cloud is shaping our heliosphere. For the other stars, of course, there are also same types of structure. They are called astrospheres. And in this picture here, you can see three nice examples of such astrospheres recently imaged by the best telescopes. And you can see from these three examples the big diversity. I mean, all these astrospheres are different because they are governed by the stellar type, the type of medium which is the star is going through, and the speed of the star, the environment. So all are different. Here, as an example, you can see on the top left a young star which is going very fast, traveling very fast through the Orion Nebula. And you can see very nicely the structure. This is HST. And on the top right, you can see a very different example of a complex binary system where this system is ejecting a very dense wind forming a peculiar shape. And at the bottom, you see the tail, which is as long as 10 light years, which is left behind the nearby star Myra, which is seen by which has been imaged by the GALEX spacecraft in a far UV. But these three cases and all the image cases of the astrosphere are extreme cases. There is no way to get such images for our heliosphere, and the reason is, well, there are many reasons, is that first, the solar wind is very weak, is among the weakest winds. The speed of the sun through the ambient medium is low, is small, and especially we are going through a very tenuous interstellar cloud. And we are in a very quiet environment, no bright star around to illuminate the scene. So this is why we are unable to get those images. But this is where having images of the heliosphere by IBEX is so exciting because, thanks to this beautiful idea to replace the photons by energetic neutral atoms has allowed to get such an image. Okay, going back to this image that you have seen previously, maybe the most exciting is the ribbon, the spectacular ribbon that you can see. This ribbon was totally unexpected, and the axis of the ribbon, as Dave mentioned, corresponds to the direction which has been inferred to be very likely the direction of the ambient interstellar magnetic field, the magnetic field around the heliosphere. And as a matter of fact, an experiment on board the SOHO spacecraft, called SWAN, has demonstrated that our heliosphere is very strongly distorted and very likely under the action of such an inclined magnetic field. And if you see that this direction of the magnetic field is offset, is completely different from the direction of motion, you can see our heliosphere here as a gigantic interstellar magnetic compass. I mean, in the same way a needle is orientated by the Earth's magnetic field, here the orientation taken by the nose of our heliosphere gives you the direction of the ambient interstellar magnetic field. So even if this ribbon is organized around the ambient field, as Dave said, it is not understood. And this is also very exciting because it is calling for a new physics. And also, well, this new physics will evidently apply to the other system, to the other astrosphere, and this is extremely interesting too. Okay, Lindsay now will tell us about our heliosphere and how it is a comfortable location.
Okay, so the heliosphere is our home in the galaxy, and our sun actually does orbit the center of the galaxy. Please roll the movie, and I'm going to show you how the sun and all the stars actually bob up and down through the galaxy as they orbit, taking hundreds of millions of years to go around. The heliosphere comes up, you'll see it in just a moment, and as Dave and Rosine have said, it orbits around the center of the galaxy. Here it is here. It's going to pass through regions that are denser and less dense. As it passes through regions that are denser, the heliosphere shrinks. And then as it passes through regions that are less dense, it's actually able to expand. So these regions that it passes through help change the size and shape of the heliosphere over long periods of time. Also, the sun's solar wind actually varies, causing the heliosphere to breathe periodically. That, along with the magnetic field that we've just been discussing, all of those factors and possibly other ones contribute to the shape of our home in the galaxy. Now, this heliosphere is very important to us because it helps protect us from dangerous cosmic rays that come from outside of the outside of the heliosphere. And those cosmic rays, as they come nearby, are deflected. So if you show the graph, you can see on this picture the fraction of cosmic rays that are able to penetrate into the solar system. It starts out at a very high percent, and then as it moves through the heliosphere, many of them are deflected, and only a small percentage are able to make it into the inner solar system. Fortunately for us, Earth's magnetic field is usually able to protect life on Earth from these dangerous cosmic rays. However, astronauts on deep space missions aren't able to bring the Earth's protection with them. So having the IBEX data and being able to understand this protection around us is really going to be critical. Now, this is a snapshot as we are today, and NASA has actually been observing higher and higher levels of cosmic rays. But in the distant past and in the far future, since the heliosphere may change in size and shape, the heliosphere might one day, or maybe in the past, has shrunk down so small that it's inside of the Earth's orbit, exposing the Earth to many more cosmic rays. Having all these new data and being able to come up with new ideas about how the heliosphere works is really exciting and helping us understand our home in the galaxy. With that, Don is now going to tell us about some other observations that complement the IBEX observations.
Thanks, Lindsay. Well, while IBEX was being built and put together, there was another mission already in flight, the Cassini mission, which was orbiting Saturn. It was launched in 1997. Cassini has on board an energetic neutral atom imager, which was designed to image the magnetosphere of Saturn, but it's not particular. It'll image any ENA that happened to come its way. The graphic we have here shows Saturn and Cassini's relationship to the heliosphere. The Earth is at 1 astronomical unit from the Sun. Saturn's at 10 astronomical units. It's a long ways from the Sun, but it's not very far from the center of the heliosphere on heliospheric distances. So the perspective from Saturn, from Cassini, is very similar to that IBEX has. The operations of that spacecraft were different. Its main object of interest is Saturn and the Saturn system, so it was doing a lot of pointing at Saturn. Not a very good place to look if you're trying to image ENAs from the heliosphere. But over the course of the years that we've been there, the spacecraft's been in orbit at Saturn since mid-2004, and we actually began this process a little before that in late 2003 until the present. We've been able to get enough snapshots of the sky from looking away to get the next graphic, which is an image which is built up over those years using the ion and neutral camera on the Cassini spacecraft. Now, this is in the same general format as the IBEX data was shown to you before, a little different color bar. You can see that central bar of emission coming down through the nose of the heliosphere in this image. It's a little different from the IBEX, but actually very similar to the highest energy channels on IBEX. The INCUS sensor starts off at about 8 kilovolts, which is about a factor of 2 higher in energy than the highest energy channel on IBEX. So this is very complementary to IBEX. And the fact that we see a structure that's extremely similar to what the high energy channels on IBEX show is a very good confirmation of those results right off the bat. Now, you can see, if you squint, that there's a Voyager 1 and Voyager 2. They're in the same position in this diagram as they were shown earlier. And those two are actually seeing on the fringes of this broader feature that you see at the high energies. But the other interesting feature of this diagram are the two blue areas. Those are voids where there's very little emission. And this is where we think that the local interstellar magnetic field points. It's very similar to what Dave was talking about earlier. If we look at the next graphic, this is the same data, but now displayed in galactic coordinates. And in galactic, if we were to show the galaxy that Lindsay showed and that Eric showed earlier in this coordinate system, it would just be a horizontal line. You'd be looking at it edge on. But so our data is broader than that feature, and it's also at a bit of an angle. It's not exactly aligned with the galaxy, but neither is the local interstellar magnetic field exactly aligned with the poles of the galactic plane. So, so this is, again, consistent with that. What it also shows is that we have a fairly continuous belt of emission at these energies that goes all the way around the globe. And if I can go then back to the previous graphic, I wanted to also point out that the Voyagers are there. At these energies, the emission is broad enough to include the Voyagers, so it's entirely relevant to consider this to be a global map of what Voyagers see. We have, with the Inca sensor, energies that go up to the energies that the Voyager sensors measure in situ. So we essentially bridge the energy gap between where IBEX leaves off and where Voyager picks up, measuring the particles, the energetic particles that are producing pressure out in this medium. And the combined information from all three missions allows us to get a pressure of those particles out there, and therefore understand better the relationship of the magnetic field containment of the interstellar magnetic field to the particle pressure that's outside the termination shock of the heliosphere. So Dave, I'd like to turn it back to you for that.
Yeah, thanks, Don. These are all really exciting results. I just wanted to bring you back to the main discoveries. So what we've observed with IBEX is this really narrow ribbon of strong emission, lots of particles, lots of neutral atoms coming in from the interaction at the edge of our heliosphere, the edge of our solar system. This ribbon winds between the two Voyager spacecraft and wasn't observed by either of them. They were both out there making these local observations and had no idea that the main storm, in some sense, was running right down between them. The ribbon is very narrow, has a lot of fine structure in it, meaning that somehow the particles are confined in very, very localized regions. We have no idea how that can happen. It's aligned by and dominated by the external magnetic field, as Rosine talked about at some length. That's a huge clue as to what's going on, but even when we put that magnetic field into our models and our theories, it doesn't produce this bright ENA ribbon. So still we're missing some really fundamental aspect of the interaction, some fundamental physics that's missing from our understanding. So what's next? We're obviously working on that. The theorists and modelers are going like crazy trying to make this connection and figure out what got left out and how it's really working. At the same time, IBEX continues to spin away and keep repointing around the sun like we talked about. We're already partway through the second sky map. And while the ribbon is still there, there's some suggestion that it's actually slightly different and maybe evolving over the 6 months between the image that we've published now and the next images. So it's really going to be fascinating to watch this feature potentially change over the years and maybe over the solar cycle. And so with that, Dwayne?
Okay, thank you all. And again, we will open it up for questions, and my apologies to the TV audience and our presenters for the construction noise. When you have live TV, sometimes things happen, but perhaps we can send that drill out to the heliosphere. I don't know. So, let's see. Well, I have some questions that have come in on my monitor here, and the three from one of the several space.coms out there in TV land. So, Dave, I think this one's for you and maybe to the team members. What's the next step with this data for the science team?
So the next step with this data that we've published today in Science in this coordinated set of papers is to really go through all of the detailed observations and rack them up against the different theories and models to try to really come to an understanding of which of these theories and models, are a good starting point for the understanding that we have and which need more modification. And really to go try to find what thing it is that we've all just kind of been, I bet it'll be obvious in retrospect, so often these things are, but that we've been leaving out of this sort of interaction. So that's really the next main effort, I think, for the team.
And I believe this question comes in, this is for Richard Fisher. The cost of the mission and how IBEX fits into the heliophysics portfolio.
That's a good question. Let me start out by saying that in the heliophysics portfolio, we try to have a mix of missions, and these range from things like sounding rockets, which are relatively inexpensive, up to major missions, perhaps even someday a flagship type mission that will explore the inner part of the heliosphere around the sun. And IBEX is from a class of missions called SMEX, Small Explorers. There was a mission cap set on this one. I'm going to look at Dave, and I'm going to say it was around $90 million. Am I about right at that? And the cost of our launchers are running around $40 million. So the total cost is in the neighborhood of $130 million. This is a small space flight mission for us.
Okay. And a question here from one of the network.coms, and I believe this is going to give everyone an opportunity. They want to know, what is your personal feelings, reaction when you saw this data and the possibilities? So, Eric, you want a personal reaction and
Well,
as a scientist?
having worked on Voyager for many years, I mean, my first reaction was, wow, the Voyagers missed it. The most interesting part of this interaction region, the Voyagers miss. And that was surprising, exciting. We've got a lot to learn.
Shall I go next?
Yeah, go ahead. Yeah, we're going to hear it.
So I guess my first reaction was terror. Because as we started to get these swaths back, and it's sort of like you get mail once a week, and in the mail you get the next swath, and you look at it and you go, no, that cannot be right. There's some background, there's some noise. We haven't done something right. Something's wrong. What's wrong? How do we fix it so that we can actually do the mission that we're supposed to be doing? And it was actually over many, many weeks, and in fact months, as these new swaths came in, and as they started not to all be at the same spin phase for the spacecraft, but wind up along at different angles and have different fine structure and all that, it was actually quite a long time before we convinced ourselves that we were right and that all of what we thought before was wrong. But there was a long time there where that was not where we started, and it was kind of a scary time for me.
Rosine?
Well, very shortly, my first reaction was wrong, because I thought that we were seeing something I have worked on, which is, we know that the sun will leave our small cloud, and there is a next cloud it will enter very well soon. It should enter one day, and we don't know if the two clouds are touching each other. If they do, because one is faster than our cloud, there must be an interstellar shock. So when I saw that, maybe we see some feature apparent to this interstellar shock. But that was for 5 minutes only. Then I realized it has nothing to do.
I certainly looked at it, and because it looked nothing like any of the initial predicted maps, I said, what is that, and how am I going to explain it to people? Because as the education person on the team, I know that my job is going to be explaining this ribbon, and I, of course, have to wait for people to figure out what it is, but then to come up with some easy ways to explain it, to show it in our planetarium show, to make a model of it that people can touch and feel and experiment with. So my questions are still going.
Well, I think my reaction was somewhat similar to Dave's in that I didn't see it coming in day by day, but I was doing this independent measurement with the Cassini spacecraft and trying to put together this sky map, and it was quite a job. It's a different kind of a mission. We're pointing all over the place. We have to motion compensate everything on the spacecraft. We've got to get the right frame. It was quite a lot of software to develop, and so every time I'd see a new map, I'd say, that can't be right, and a lot of times it wasn't. But toward the end, we started getting very consistent results, and then when we started comparing them with IBEX, and we're getting very consistent results with IBEX, that's when my confidence grew in what we were doing, and it's really turned out to be a treasure, so very happy with it.
Well, Lindsay, from there, when I can hear my earpiece, you guys are doing a really good job explaining it. So I believe we're going to go take a question on the phone from Irene from Discovery. Irene?
Hi, thanks very much. I just had a question for Lindsay. I was struck by your comment about the possible changes in the heliosphere, and I was just wondering if you or some of your colleagues there might elaborate on what sort of what would have to happen to the sun to have the heliosphere smaller within the orbit of, or even shorter length than the Earth's orbit. Thanks.
Okay, well, I'll start. What would really have to happen, as Rosine was mentioning, is that we would have to clear out of our current environment and pass into an area of gas and dust that is much, much denser than the part we're currently in. And that would cause the heliosphere to shrink in. And after that, I don't know, Dave, if you have...
I guess I'd like to comment too. I mean, the size and shape of this heliosphere is driven by two things. It's inflated from the inside by the solar wind, and it's squeezed from the outside by the magnetic field and by the motion through the local environment. And so it's sort of a balance between those two. And so while the sun could change and put out much, much less solar wind than theoretically possible, the most likely thing, and I think it's happened probably many times over the history of our solar system, as we've gone around the galaxy up and down and passed through the dense regions with stronger fields and that sort of thing, is that this heliosphere has shrunk and grown and changed shape and really changed the amount of shielding that we get from the galactic cosmic rays out in the galaxy. Anybody else want to comment on that?
Well, just sort of one interesting thing. When the Voyagers launched in 1977, they actually thought that the heliosphere wasn't much bigger than the orbit of Jupiter. It was very much smaller. And the joke in the community was that the estimates of the size were getting bigger at almost exactly the rate the Voyagers were moving away from the sun, because we kept on not getting it, but we were going to get there real soon now. So it's only when the Voyager 1 actually crossed the termination shock, the first boundary, that in 2005, that we really knew that what the size of the heliosphere was.
Okay, I think that's going to do it. You guys definitely did a great job explaining it. For further information, as always, go to www.nasa.gov. My congratulations to the team. And of course, as I said, with all of the science mission divisions, and it especially happens here in heliophysics, science never sleeps. Thanks for joining us.